Hey guys, Mr. Davis here. I wanted to make this video as a review of some of the material that AP and the AP Environmental Science program considers to be essential core knowledge that you should have going into AP Environmental Science. These should be things that are kind of a review from previous science courses, including biology and chemistry. And the school, the district, and the AP all say that you should have had general high school bio and chem. But I want to review some of the core content that you will use in this class, all right? You won't use it all the time, but this is stuff that's just kind of expected to be known, and it will pop up from time to time in class, all right? So without further ado, I'm going to try and go through this quickly. I'm going to post this video on YouTube, so it'll be able to be reviewed anytime you want, and I will, of course, recommend several times that you review it at different times of the year, particularly before tests, especially finals and things like that. All right, so let's take a look. All right, first off, how about a little chemistry review? You should know what an isotope is, which is when you have two atoms that are the same element, like carbon or nitrogen, and they have the same atomic number because they have the same number of protons, but they have a different mass because they have a different number of neutrons. All right. So remember, key terms here are protons, neutrons, and electrons. Protons have a positive charge, pro-positive. Neutrons have a neutral charge, and electrons have a negative charge because we can only have two things that have an N in them when we're naming stuff. No, I don't know, but yeah. An ion, then, is an atom or molecule with a positive or negative charge because it has gained or lost an electron, all right? And then lastly, you have pH. pH is measured on a scale from 0 to 14, and it is a measurement of how acidic or basic a solution is. The more acidic a solution is, the more hydrogen ions it will have. And that's just a proton without an electron. And yes, it can exist, especially in aqueous solutions. It is unbonded and it wants to attack things and get an electron really, really badly. So that is why it behaves like an acid, basically. You have, as a scale of 0, the most acidic stuff, and that's battery acid. All right, it's a logarithmic scale, so a 0 is the most acidic something can be. On the other hand, at 14, you have the most basic things, stuff like concentrated bleach, drain cleaner, high power solvents. Typical characteristics of basic solutions are they feel slippery or taste bitter. Whereas on the other side, things that are acidic taste sour and can feel drying on the skin, all right, or burning, depending on how basic they are. So when I'm talking about acid rain or things like that later on, and I say that the pH is lowered, that means it's becoming more acidic, all right? And then right in the middle at 7 is pure water. That's pure water with nothing in it. Now, seawater is a buffered solution that is already slightly basic, but as it shifts towards acidic, that can cause a lot of problems for animals. And we will discuss that when we talk about ocean acidification. All right, then you have organic compounds. And when I say an organic compound, I don't just mean things that are, certified organic or whatever. No, no, no. When I'm talking about organic compounds, what I mean are carbon-based compounds. They have at least 2 carbon atoms combined with each other, and usually some other elements. The one exception to this is methane, which is CH4, which is considered a organic compound, but it has 1 carbon, and then all of its available slots are filled up. All of its available bonding locations are filled up with hydrogen. Hydrocarbons are made of primarily carbon and hydrogen. Most oils, gasolines, plastics, things like that are hydrocarbons. Chlorinated hydrocarbons contain carbon, hydrogen, and chlorine, and that can be things like DDT. Then you have other carbon compounds like carbohydrates, which are sugars, or complex carbohydrates, which are a linking of multiple sugars. And if you look over there, what you'll see is I've got one chlorinated compound, that's DDT, and the other one there is glucose. So yeah, these are some common hydrocarbon groups. All right, we already talked about this one. We had a video on it, but this is one of those ones that you should also know, and I'm going to review it here. So a feedback loop is any time that energy or matter or information coming out of a system is put back in, and that causes further changes to the system. So a positive feedback loop causes the change to accelerate. A negative feedback loop causes it to go back to baseline. All right, and I've got a couple of examples there, and we've done some examples in class. Just keep in mind that negative feedback loops are self-correcting back to equilibrium. Positive feedback loops kind of spiral outwards and become more and more extreme. Remember, positive and negative, those terms are not subject to if the effect is good or bad. So don't say, oh, this is bad, so therefore it's a negative feedback loop. No, no, that is not how it works. Okay? Do not associate that with value judgments. Okay, here's one that was not in any of our videos yet, but it's an important thing to know, and it will pop up from time to time. Delays and thresholds. All right? So a delay is just what it sounds like. A lot of times you won't see a change in a system until, it's gone on for a little bit. All right? So we may not notice an effect on a local climate or habitat or something if we cut down one tree, but if we take one tree every day, eventually that's going to add up. And heck, even after we take all of the trees, we might not notice an effect right away. It might be a while until we realize all of a sudden we've got horrible soil erosion and stuff like that. Another one was DDT accumulation. All right, DDT was used for years before any negative effects were seen in the biosphere, and then when it was out of control. Threshold levels, though, are a tipping point where a fundamental shift in a system or behavior happens. Okay, where once you get past a certain point, all of a sudden everything's changes. All right, so we have stuff like population growth, greenhouse effects, leaks in toxic waste dumps, things like that, and we'll talk about one of them. Love Canal is one of the first ones, and everything was fine, and there was some slightly elevated level, wasn't a big deal, until all of a sudden a big event happened, and that clearly changed things. All right. So let's talk about what a nuclear change is. So this is shifting gears a little bit to some review of chemistry. So a chemical change is a change in how different molecules bond together. A nuclear change, though, is a change in an element itself. Nuclear changes occur when the nuclei of certain isotopes spontaneously change or are made to change through interaction with energy. Natural radioactive decay is a nuclear change that occurs because the isotope is unstable. All right, the balance of protons and neutrons in the nucleus of that atom is just fundamentally unstable, and it pops apart. It will release energy when it does that, and that can then further necessitate change in other unstable isotopes, and that's nuclear fission. If you control nuclear fission, you get power. You can use that to generate heat, which can then be used to generate energy. If you have uncontrolled nuclear fission, that's how you get thermonuclear weapons. All right? So there's a little bit of a difference there. All right? That brings us to half-life. Now, naturally radioactive elements occur. All right? They decay over time as a result of these unstable nuclei. The reaction is not affected by temperature, pressure, or the presence of other chemical substances. So if you put them in acid, nothing happens. All right? Radioactive decay follows what are called first-order reaction kinetics. Basically, it just reacts at a steady rate. All right? It doesn't speed up. It doesn't slow down. It follows a steady rate. Half-lives are the length of time that it takes for half of the sample to undergo that decay. So it takes about 10 half-lives for something to be considered safe. So if we create plutonium-239, one half-life is 24,000 years. So in order for it to be safe, it has to be stored for 250,000 years. And when we get to our section on energy, we'll talk about this as a serious concern when talking about nuclear power. All right, how about energy itself? What is energy? Energy is the ability to do work and transfer heat. It can be electrical, mechanical, it can be electromagnetic in the form of light. It can be radiation, which is another form of electromagnetic energy. It can be heat. There's chemical energy, all kinds of stuff. So, for example, humans need about 2,000 kilocalories a day, which is what we call the 2,000 calorie diet. That's all chemical energy. That is all energy stored in the chemical bonds of the food that you eat. As your body breaks that down and splits it apart, it releases energy. That's that equation for respiration, where you take in oxygen and glucose and you get 6 carbon dioxide and 6 water. The major types of energy, though, are kinetic energy. It's what matter has because of its mass, speed, and velocity. Then you have potential energy, and that's energy that is stored with the chance of doing work. So in carbon-carbon bonding of octane, when those bonds are broken, that potential energy that's stored in that carbon bond is released. It can push a piston, moving a car, and now it's kinetic energy. So that's how you can go from potential energy to kinetic energy with a chemical change. Combustion is a chemical change that releases energy. Hey, here's a weird fact. Light can be kinetic energy because photons seem to have some mass, because it's both a wave and a particle at the same time, because life wasn't confusing enough already. All right, thermodynamics and you. We already have talked about these in class, but it's very important that you understand the first and second law of thermodynamics. First law of thermodynamics is just like the law of conservation of matter. Energy can never be created or destroyed, only rearranged and changed shape. Hey, special relativity, E equals mc squared, actually confirms this, where energy is just matter in a different state, and matter is just energy bound up in a solid state. Yep, they're the same thing. Then you have the second law of thermodynamics. Now remember, energy can never be created or destroyed, but chaos and disorder can increase. So with every transformation of energy, the usefulness of it decays. So an example of this one is a car's gasoline energy, the chemical energy stored in the gasoline. Only 6% of that energy is actually used to move the car forward. The rest of it is turned into heat, which your car has to then get rid of through its radiator. So yeah, that's a lot of waste energy. Now, that energy doesn't cease to exist. It just is dissipated to the surrounding environment. It goes to the, surrounding air, basically. It's transferred by that radiator to the air. It doesn't cease to exist. It just gets spread out, all right? The second law of thermodynamics will eventually be responsible for the cold, slow heat death of the universe, when all stars have burned out and the entire universe subsides to a background temperature, just a handful of degrees above absolute zero. Depressing ending, but yeah, that's how the universe will end eventually, we think. Hey, so here's some problems though. Because of the second law of thermodynamics, energy efficiency is a measure then of how much useful work is accomplished. Okay, so how much of the energy that you create actually goes into that work, and how much of it is wasted as heat, or just goes into useless things, is held back by friction, any number of things like that. So in the United States, only 16% of the energy that we create on any given day is actually used to do work. The rest is either wasted as heat in other forms or just simply not used efficiently. Examples of this: energy in your house as electricity. Just pushing that electricity through the wires in your house, there is some resistance, and that resistance is a loss of energy. As your air conditioner works, it is not a 100% efficient system. It takes more energy to cool down your house than the amount of energy stored in that heat. So it has to be pumped somewhere, and we basically just shove it outside, and we lose some energy there. On our electrical grid, if we generate too much electricity, it's just grounded. It's sent literally just into the ground, like lightning strikes the ground, and it dissipates out that way because we can't use it. So there's plenty of room for improvements. Could be energy efficient appliances, could be utilization of more renewable energy, could be harvesting of energy better, or just smart grid technology that makes sure that we don't waste any or generate more energy than we need. All right, whole bunch of things there, and when we get to our section on electricity, we'll talk about this one a lot. Okay, here's a couple other things that are definitely worth reviewing, and again, I'm going fast here. I'm trying to get through this, and this is the last thing I've got for you. You should be familiar with the metric system, all right? Metric system is something that you have been taught all the way up through school. It's been reviewed in every science class that you have taken. You need to be familiar with the standard units of measurement, okay? So if I'm measuring length, if I'm measuring volume, if I'm measuring mass, those kind of things you should be familiar with the metric system. So, liters, grams, and meters. All right, you need to be familiar with them. You should also be familiar with temperature in Celsius and Kelvin. You know, it's just roughly familiar with them. Okay. You need to know the prefixes. All right, so you should know what a kilometer is, or a centimeter, or a millimeter. All right, you need to be familiar with those prefixes and how to convert between them. There's the acronym, the mnemonic device, King Henry died by drinking chocolate milk, or whatever. You can look that up. You should be familiar with that. That's knowledge you're expected to have at the start. All right. You'll generally get some review on that, but I mean, this really is stuff that we should know, because I remember, like, I used to teach 7th grade science. You know, I taught them this all the time. All right. We haven't shown. We have shown it in class, but we haven't put it in here. You should know the formulas for photosynthesis and cellular respiration. All right. You should be able to show the prefixes of those. All right. So you need to know, carbon dioxide and water in the presence of sunlight creates glucose and oxygen. All right, and you should be able to balance that. It's 6 carbon dioxide plus 6 water creates 1 glucose and 6 oxygen molecules. You should know that as photosynthesis. Then cellular respiration is just the reverse of that. If you combine sugar and oxygen, it burns and produces water and carbon dioxide as its byproducts. All right, you need to know those. All right, we have covered them in class. They were covered in the biogeochemical cycles. They were hinted at in primary production. You need to make sure you know that. All right. And then lastly, I think you should be familiar with the 5 kingdoms and roughly what they do. So archaeobacteria, which are your extremophile bacteria that live in extreme environments. Eubacteria, which are your true bacteria. They're the ones that can make you sick. Plantae, which are plants, multicellular photosynthetic organisms. Fungia, which are your fungus, mushrooms, things like that. They cannot photosynthesize, and they have a cell wall that is made of chitin. They're more like a weird cross between plants and animals. They've got more in common with animals, though. And then that brings us to Animalia, which is the animal kingdom, which is, all vertebrates and invertebrates. And then you got one last one, and that's Protista. Those are things like amoebas, which are single-celled organisms that have internal cell membranes. So they have a nucleus and organelles and things like that. So you should know the general 5 kingdoms of life. All right. All right, guys, that's what I've got for you. That should cover what you need to know. As the background information, again, I wanted to make this quick. That's it for now. All right, guys, take care. Have a great day. See you soon. Bye.